Hello and welcome back to Real Analysis. And as always, first many thanks to all the nice people that support this channel on Steady or PayPal. Now today in part 30 we will talk about an important property continuous functions have. More concretely, we will show that a continuous function conserves the property compact. In general, for a map you should imagine a domain on the left and a codomain on the right. Of course, in our case, in real analysis, this would be just subsets of the real numbers. And now here we have a map or a function that is continuous. Okay, now if we start on the left hand side with a compact set A, then this set is mapped to the right hand side where we find a subset we call the image of A. And the notation I use is f with square brackets of A. Now if we put in that A is compact, then the image is still compact. And we have this because we know f is continuous. Okay, this is the topic for today, so let's formulate this with a theorem. Here in our course I always used I for the domain of a function. And now this I as a subset of R should be compact. Moreover, the function f we consider here should be continuous at all points. So these are the assumptions we need, and then our conclusion is that the image of I is also compact. Here, please don't worry, we will recapitulate everything about compactness. The first thing would be the famous Heine-Borel theorem, which tells us that a compact set in the real number line is exactly bounded and closed. If you want to look it up again, this was part 14. Now with this in mind, we get even more out of this result when you think of the graph of the function. Here's a simple sketch where our domain I is a bounded closed interval. And then on the y-axis for this example we find this image here. Now like for all subsets of the real numbers, we find here the supremum of the set and here the infimum. However, here we already know the image is bounded and closed. Hence the supremum and the infimum are elements of the set itself. And of course, you already know, in this case we call them maximum and minimum respectively. Therefore, we get the nice result that the function has a maximal value and a minimal value. Using symbols, this reads that we find two numbers x plus and x minus, of course coming from the domain I, with the property that if you put them into the function, you get the maximum and the minimum respectively. Of course, this property seems natural, but in general it's not correct for a non-continuous function. Maybe it's a good exercise for you to find a counterexample. However, if we work with a continuous function, everything is nice, we have the maximum and the minimum. Now for our example on the right hand side we find x minus here and x plus here. They don't need to lie on the boundary of I, and they also don't need to be unique. Of course, there could be different numbers that get the same value. Okay, now I think we are ready for the proof of this statement. For this, let's recall the definition of a compact set again. Now, compact for a set means if you choose any sequence with elements from this set, there is a convergent subsequence where the limit lies also in this set. In short, to remember it, every sequence has a convergent subsequence. And now for this reason, here we should start with a sequence yn. Of course, the elements should come from the image we are interested in. Now, since yn is in the image, we simply know by the definition of a map there is a point xn that is mapped to yn. And of course, this whole reasoning here works for all yn. Which means we get a new sequence with elements from I. And that is something we can work with because I is compact by assumption. More concretely, the definition of compactness now tells us that this sequence has a convergent subsequence. Now you already used two subsequences where we need a second index and we usually call it k. Here we know for this subsequence it makes sense to send k to infinity, because what comes out here is an element of I. Let's give the point a name, let's simply call it x. Okay, please note here, this is something that happens on the x-axis. But of course, we can simply translate that to the y-axis by using the function f. And there the continuity helps us. Now, simply by definition, we have that y and k is equal to f of x and k. And here we can ask ourselves if this sequence is also convergent. So for this, let's put the limit in front of both sides. Please note here, we don't know yet if this makes sense. But of course, we will see it in a few seconds. Because in the next step, we can put in that f is continuous, which means we can pull in the limit. And here we already know this exists. Hence, by the definition of the continuity, we also know that the sequence of the images needs to be convergent as well. And this image f of x we can simply call y. And with this, you should see we have everything we need for compactness. Okay, so let's summarize that in a conclusion here. So our subsequence y and k is convergent and its limit y lies in the image f of I. And therefore f of I is compact. And therefore we have shown what we wanted to show in this video. So please remember this important result here. Images of compact sets are also compact if we consider a continuous function. And an important implication from this is that a continuous function defined on a compact set always attains its maximum and its minimum. In fact, we will often use this property later. Okay, with this, I hope I see you in the next video. Bye!